Welcome to Brain Vision.
Hi there. So for this problem, we need to calculate the magnetic and direction of the magnetic field that this electron produces at some given points. Each of them are at the distance r of 2 micrometers, and the electron has a velocity of 0.1 times the speed of light. So the first question is to calculate the magnetic field at a point A and B. First, we can see from the figure the point B is at some given angle from the electron. To obtain the magnetic field for all of these points, we are going to use the magnetic field produced by a moving charge, and that formula or equation is the following. Where the angle theta is the angle between the vector of the velocity with the vector of the distance to the point where we want to measure the electric field. So the magnitude can be obtained from this expression, and the direction can be obtained from the right-hand rule. So first we are going to obtain the magnitude. In this case for A, we're going to call this for A, is mu, and the permeability of free space over 4. The charge in this case is the same for everyone, and we are trading with electron, and we can see that the vector r from the electron to the point form an angle of 30 degrees, because if this angle is 60 degrees, and we know that the angle that form the two axes is 90 degrees, we just subtract from 90 degrees 60 degrees, and that gives us the 30 degrees that we want. And everything else is just what we are given for this problem. So we are going to substitute all of those values. We know that the permeability of free space, it's 4 pi times 10 to the minus 7 newtons per second square over coulomb square. All of this over 4 pi. And the charge corresponds to the charge of an electron, which is 1.6 times 10 to the minus 19 coulomb. And the velocity of this electron is given as 0.1, the speed of light. We also know that the speed of light is 3 times 10 to the 8 meters per second. So we put that in here, 10 to the 8 meters per second. And the angle, as we said, is 30 degrees. And the distance to that point is 2 micrometers, which is 2 times 10 to the minus 6 meters. With all of this, we obtain a value of, remember that the distance is to the square, and this gives us 6 times 10 to the minus 8 Tesla. That's the units of the electric field. So that's for this point. And the direction could be obtained by the right-hand side. And that is given by the product between the vector, the velocity vector, and the r vector. So the right-hand side is that you put your right-hand side, right-hand hand in the direction of the b vector, and you go from there to just the r vector, and you will see that your thumb is pointing inward. So it is inward. If we put like another axis, it is going to point in this direction inward. And if we set this as positive and this as negative, I'm going to put this positive and this negative, then it will be negative. And direction inward or negative if you set it in that way. Now for part B, for this same part, but to obtain the magnitude of the electric field for the point B, we will have that the angle between the vector B and the angle between the distance, the vector, the position vector of the point B, it's, if we need to sum all of this, we need to sum 90 degrees, and put in another color. You need to sum this 90 degrees and also this 60 degrees. So we will have 90 plus 60 degrees, that's 150 degrees. So with that in mind, we just simply need to put all of those values in here. So we have the permeability of free space over 4 pi. Everything else is just the same as before. The velocity, the speed of the electron, the same. But what changes is the angle between these two is 150 degrees. And the distance is also the same because it is stated in the problem that all these points are at a distance of 2 times 10 to the minus 6 meters square, of course. And if we introduce all of this information into the calculator, we obtain a value of, again, 6 times 10 to the minus 8 Tesla. Now, the direction, again, we put our right hand side, our right hand in the direction of B, and we go from there to the vector R, And we will see that again, that direction is inward. So we will have something like a vector inward. So as I said before, if we set that as the negative, you will have a negative inward or inward the page as you wanted to put it. Now, part B of this problem is the magnetic field in the point C. So this is more straightforward. The point C is in the x-axis, so it will form with the vector B 90 degrees. So we have that. And we're going to put everything as just as before. Yes, so we'll have the same. The only thing that changes is the angle between them that we said it is 90 degrees. And we know that the sine of 90 degrees is just 1. So from here, we obtain a value of 1.2 times 10 to the minus 7 Tesla. And the direction, again, we put our hand in the velocity vector and go from there to the r vector. And again, it gives us a vector inward. So direction inward, if we set that as the negative, we obtain a negative bar. And finally, part C of this problem is the vector, the magnitude of the magnetic field in the point D, so that we can see from the figure that we need to go to obtain the angle, we need to go from B all the way down to this point. So we know that this is 90 degrees, and then again, this is 90 degrees. So the distance to that point is, it will be the same as before, the same, all of this, but only changes the sign. And it will be the sign of 180. And we know that this is 0. So by multiplying 0 by everything else is just 0. So this is the magnetic field at the point D. So because the magnitude of the magnetic field in this point is 0, we don't need to calculate the direction because the vector is just 0. So this is it for this problem. Thank you.